R2, okay? This is the plane. Is it a field? Well, let's see. We can add two vectors. This is just vectors in R2 in the plane. We can add two vectors, get a vector. There is the zero vector, and there is the negative. We can multiply. This is an issue. Can we multiply? So if I have AB, CD, can we multiply two vectors in R2 to get a vector in R2?
No.
There's no standard thing, but I mean, you can come up with any rule for multiplication. I mean, one way of it is maybe let's multiply these together and these together, right? That's okay. This is a rule for multiplication. So if this is a rule for multiplication, do you have an identity? So do you have, if you have here AB, do you have an element, the identity element, which I don't know it yet, such that when you multiply this guy, you get the same thing again? Yeah, that's easy. This shows that E is what? 1, 1, right? Okay, so it's a vector in R2, so I have an identity. So actually, up to this point, R2 is what? No, field, you should...
A ring.
A ring, right? Very good. So up to this point, R2 is a ring. It's not a field yet. For a field, I need to show that I can divide. Let's see. So if I have AB here, that is non-zero. Non-zero. The zero element is 0, 0, right? So AB is non-zero element. Can you give me its inverse such that when I multiply, I get your identity? According to your proposed definition of multiplication, there is the identity. Okay. And now I'm asking you, with respect to this identity, do you have an inverse?
1 over A.
Well, if this is 1, 0, so 1, 0 is not 0, 0, right? If this is 1, 0, the first result will be, or the second result will be 1 over 0. So actually, no. So if I have like this is CD, and I'm looking for CD, and I have this is 1 and 0, so the element 1, 0 is non-zero. Can you give me the inverse of it? Well, this equation shows that D is 1 over 0, it's not defined. So no inverse. No inverse with respect to this multiplication. R2 is not a field, R2 is a ring. It's like integers. Okay? Any question about that? And then it came what I call, this is not the standard name for it, but it's my name. The magic multiplication rule. You have two vectors in R2, A, B, C, D, and someone magically came and said, I'll give you a way to multiply these two guys. I'll multiply it the following way. A, C minus BD. And here is AD plus BC. Well, that's okay. I mean, I will go and check the axioms. This is a very weird thing. I'll see if it's ever useful or not, right? Let's check the axioms. Can you provide me with an identity, please? So AB times something, I get the AB again according to this rule. Yeah. So this is the identity. Yes, it's actually 1 and 0. And you can check it very easily. Okay, what about the M? So far, it's a ring under this multiplication. Can we divide? If I give you AB, and this guy, I don't know it, I recover your identity back. Can you give me this guy? Yes, it's actually A divided by A squared plus B squared, negative B divided by A squared plus B squared. Here I'm dividing by what? A squared plus B squared, right? So for the denominator to be 0, both have to be 0, which means it's a 0 element. And here we should say this for a non-zero element, right? So this is a field. So actually R2 with this magic multiplication is a field. It's like the real again. And this field we call it the complex numbers. Right? And it is this magic multiplication rule that actually led to all the results in very weird and super interesting results about complex analysis. For example, differentiation. You guys know that a function f from R to R, I did not define this in this course so yet. So anybody has an issue with this, there's no shame. This means a function that takes an element in R, just a number, and gives you back an element in R. This is the input space, this is the output space. So it's like all the functions that we know, sine, cosine, anything. Okay, so a function, the usual function that we know is differentiable at x if what? You remember? The limit as h goes to 0, f of x plus h minus f of x divided by h. This limit exists. Exists means it's less than infinite, right? It doesn't go. Okay, this is a number, and the function takes a number, gives you a number, so this is a number, yes, and this is another number. Yeah, I can subtract, because it's a field. We're working in R is a field, and I can define. That's very good. Well defined, everything is good, and if this is really exists, then it is the derivative. If this guy is some number, then this number is the derivative f prime of x, right? Okay. Let's go to see the definition of differentiability in R2, a function. If from R2, so it takes two numbers, right? Takes a vector, gives you two other numbers, is differentiable at x if what? To make the analogy, I will modify this definition a little bit. I will take A and get it inside, okay? So I will have actually here minus AH is 0, right? So a function here, a function from R to R is differentiable at x if there exists some number A such that we have this limit is 0, okay? And this number A will be the derivative, which is the linear approximation of the function. Just the slope of the function, right? Very good. The same here, we'll do the same. So this function is differentiable at x if there exists some A. I will have a big A here because we're 2 by 2. So A is a matrix, actually 2 by 2 matrix, such that the limit as h goes to 0, f of x plus h minus f of x minus A times h divided by h. Look at this. F takes a vector and gives you a vector. This is two numbers, vector and R2, vector and R2. A vector and R2. This is why this is a matrix times a vector gives you a vector. Everything here is a vector. H itself is a vector, and I cannot divide vectors because vectors are not field. It's not field. I cannot leave it like this. This is like rubbish. This is like nothing. So this is why the very formal definition that you find in books is that I divide by the modulus. And this has serious consequences. Why? Because now, if you care about the modulus and not the direction, you don't have directionality. You don't have directionality. So you can have a function that is smooth, differentiable along x, and along y, but the function is not differentiable. You don't have directionality. Whereas, look at the definition in the complex. A function f that takes the same two numbers but viewed with respect to the complex, which means we have multiplication and division. So it's the same two numbers. Remember, R2 is the same as the complex plane. It's the exact same number of points, the exact same addition rule, everything is the same, they are isomorphic to each other, they look like each other, everything is the same, except here we have a magic multiplication rule that allows division, so it's a field. So a function from C to C takes the two numbers, gives you two numbers, is differentiable at x if there exists A such that the limit f of x plus h is two numbers, minus f of x, two numbers, minus AH2 numbers divided by 2 numbers, and this is very well defined because I can divide 2 numbers in the complex plane. So now this means that I care about directionality. So in the sense, df by dz, the complex argument, along the x-axis should be the same as along the y-axis. This is actually the requirement for, if you remember, or doesn't matter now. So this statement, this red statement at the bottom is actually equivalent to, it's if and only if Cauchy-Riemann's equation is satisfied. So from where we got Cauchy-Riemann's equation is from this exact requirement. This is the equation that gives you Cauchy-Riemann's equations. And comes from where? Comes from here. Because here I can divide. I care about directionality because it's a field. And why this? Because I had a magic multiplication rule from the beginning. The Cauchy-Riemann's equation is that when you have x and y, you take 2 numbers, right? And your function will map these 2 numbers to other 2 numbers. One of them will be a function of x and y. The other one will be also a function of x and y. The Cauchy-Riemann's equations is ux equal vy and uy is negative vx. A complex function is differentiable if and only if the Cauchy-Riemann's equations are satisfied. Obviously, from this story, you can conclude that for a function to be differentiable in the complex plane is harder for it to be differentiable in the R2. I mean, for example, this is a function that takes x and y to x squared plus y squared and negative 2xy. I can view this function that takes from R2 to R2, right? Obviously, this is differentiable. I mean, you can differentiate and nothing bad about it at all. Whereas, I can view it as from C to C, right? This is not differentiable because it doesn't satisfy Cauchy-Riemann's equations because I care about directionality. Okay, so it's harder to be differentiable. It's harder to be differentiable in complex, but that's okay. Okay, we understand. Why are you making a big deal here? Because the consequences are very serious. In real line, so on R2, whatever you like, Rn, okay? On R, we have continuity, right? Your function can be continuous, function can be differentiable. Obviously, if it's differentiable, it's continuous. Can be twice differentiable, and again, if it's twice differentiable, obviously it's differentiable, and so and so. It can be infinitely differentiable, which sometimes we call smooth, right? And this implies that. And we have more. We have analyticity. Analytic. If a function is differentiable in R, it's not necessarily to be twice differentiable, right? I mean, if it's continuous, it's not differentiable. If it's differentiable, it's not necessarily twice, and so on. So even if it's infinitely differentiable, it's not necessarily analytic. I'll give you. Obviously, this function is continuous. This is the absolute value. It has a kink here, so it's not differentiable.
Professor, what is analytic?
Yeah, I will go through it right now. So this function is continuous but not differentiable. You can keep integrating and get these guys, but here, let's see what is it. We understand here, like infinitely differentiable, I can differentiate infinite number of times, like sine, cosines, or whatever. What do we mean by analytic? So analytic, we mean we have a power series. We can represent our function by this series, n equals 0 to infinity, some coefficients times x minus x naught some point, or I'm expanding around some point, to the n. And actually these coefficients are nothing but the derivatives of the function at the point. So, okay, wait a minute. First of all, this is not approximation. It's not approximation. It's exact equivalence. Okay? The function is exactly equal to this. At what point? At all points where the function is analytic. Okay, at all points. Okay, and this is what, this is like polynomials, but infinite of them. And the coefficients of the polynomial, which define the polynomial, all the polynomials look the same except for the coefficients. The coefficients that define the polynomial, they are dictated by the function value and derivatives at a single point. So the function value and the derivatives at a single point dictate the behavior of the function in the entire domain. So the local properties of the function dictate the behavior of the function in the domain. Okay? So this is a very hard requirement. So obviously this is why we have infinite differentiable functions that are not analytic, and I'm giving here a very famous example of that, which is, sometimes people call it Cauchy functions. F of x is e to the negative 1 over x, x greater than or equal to 0 and 0, x less than 0. And if you plot this function, it looks like the following. This is unreal, okay? It's 0 here, and at 0 is 0, and it's actually quite flat at 0. So the function value, as long as its derivative, as well as its second derivative, as well as all of its derivatives at 0, they are all 0 for all n. So if this function were analytic, the function and the value are all zeros, this immediately tells you that the function should be flat 0 for the domain. The function is not flat 0 for sure. So this function is not analytic. This is infinitely differentiable. I can differentiate it infinite number of times, but it's not analytic. So in real analysis, analytic is much harder requirement to get. So from any one of these to the next step is harder and harder and harder and harder. Even if it's infinitely differentiable, it's not necessarily analytic. Whereas because of that magic multiplication rule that allowed this differentiability, difference in differentiability on C now, here we were on R. Now we are on C. Differentiable, just one differentiation is exactly equivalent to analyticity. Okay? You differentiate twice, you're capable of differentiating infinite number of times, in particular you're analytic. Which lead to very interesting results that form the entire course of complex analysis. I don't have time to go all over them. I may give you one example, like something called maybe identity theory. There are very interesting results coming out of this. A function in the complex plane, if it's differentiable, we give it the name holomorphic. If it's holomorphic, meaning differentiable, then it has super nice properties. I mean, something that all of them, I can say that almost all of them are non-intuitive. You cannot expect from the beginning. Like the